experience here, I think, so much more special. I don't know, I always felt personally that I was like at the center of where new physics was created, new things were invented, and very, very exciting. Of course, all with some good toast or symbolic drinks to the successful continuation of the situation. And yes, okay. I think that now Misha sort of went a little bit to the dark side of experimental physics, that maybe he will tell us a little bit now, but it still continues to be very much the center of theory of INEMO.
All right, so thank you, Paula, for the great introduction, and it's kind of really inspiring to see all of you guys. So I kind of anticipated some of that in my talk. That's why I changed my title, and it will be now about Rydberg blockade, about quantum computing, and of course some ITAMP stories. So the field that I'm working on for the last 25 years since coming to the ITAMP is the field which is by now is often called quantum science and technology, and this really is a quest for controlling quantum objects. So in this quest, what we're trying to do is isolate and control some simple quantum objects and build more and more complex systems from them. And what we want to do with these systems is first study new physics, and this is normally the physics of engineered many-body systems, creating and probing basically entangled states of matter, but also exploring new applications. And one of them is quantum computing, but there is also quantum communication and quantum metrology. And of course, by now, this field is something that you read about in newspapers every day. But it is actually important to emphasize that it still remains a frontier of basic science, and there are some really important questions which has not been really addressed or solved. So one is the question of if and how we can build truly large-scale quantum systems containing, for example, millions of good qubits which don't make errors. But even more strikingly, there is another question: is that if I were to kind of bring, for example, a big quantum computer, I guess you guys are a very special audience. You would know what to do with that. But in general, there are very few examples what you can really do with quantum machines, which classical machines can do. And some of these things have been actually already addressed. Earlier, for example, Annabelle was talking about kind of the interplay of quantum computers and classical machine learning. It very well could be that this quantum machines will be used to train classical computers, and maybe vice versa. Classical computers can hopefully help us build better quantum machines. But I would like to kind of now step back and go to the beginning of my journey in this field, and that started kind of in the middle of 1990s. So I was a student in Texas A&M, and there's I think you probably don't recognize most of the people here. Here is Michael Fleischauer, who was then an ITAMP visit. Olga was also a visit. Paul Mandel, you probably don't know. Many of you don't know him. He was a professor in Brussels. He was actually one of the kind of pioneers in this kind of complex systems, and chaos is someone we collaborated a fair bit. And so I was finishing my PhD. I was thinking about what to do, and for reasons I will tell you in a second, someone told me, or in this situation I will explain you in a minute. So someone told me that there is this place at Harvard called ITAMP, and they have this very special postdoctoral fellowship. And so I decided to kind of inquire about it, and at the time there was early days of internet, one could read about ITAMP, and what I realized immediately is that no one in this ITAMP community was working, for example, on topics like quantum optics. And so that's my anticipation of that, what Paul was trying to here do. So in the spring, I think maybe in March of 1998, so I decided to explore. So I actually maybe wrote and even called Rick Heller, who was at the time the ITAMP director, and I didn't really get a response. And then, but there was a website, and Kate at the time was the deputy director. So I should also preface it by saying that I at the time was in Texas, and I was like a most senior student. And in Marlon's group, in Marlon Scully's group in Texas, I was basically in charge of a lot of things, including writing proposals, supervising junior students, it was actually, I did not enjoy some of these things, but it was a great experience. And so when I saw Kate on this website, so my kind of anticipation was that I would call someone who would be like a bit of my peer, So, I basically, there was a very nice picture. I could not find the picture from this time, but and I decided to ask you a few questions. And one question is, for example, does there even make sense to apply to this item position? Because I really, want to do some things which is not done here. So I did not really understand how the item works at the time. And I asked her a few questions, and she tried to answer that. Of course, we are looking for the best people from across the all fields, and I thought it was very nice and polite, but I kind of decided to probe more, and I, at the time, at some point I asked Kate, but okay, so I mean, this is great that, thank you so much for being so encouraging, but can I talk to someone who really makes decisions here? And kind of looking back, I mean, Kate was really kind of, a leader of the ITAMP for almost 2 decades, and by the time she was already, doing it for quite some time. So apparently this conversation did not go very well. So, so what I understand that afterwards, it was just this ITAMP coffee, and then Kate came out and basically started, talking to other, ITAMP people and said, "Oh, there is someone who just called me, what an asshole, Here, will be across my dead body, so Kate can tell this story better." But, somehow, I don't know how then, so I think this should have been the end of my story here, But somehow she changed her mind, I don't exactly know what happened. So at that time, we did not interview ITAMP postdocs. Maybe it was a good thing, Sorry, they did not interview. So afterwards, after I came, the decision was made to actually interview, So maybe in the interview, this would not go so well. But anyway, so this is why I think what Paulus, and Susanne was trying to kind of conspire here. So actually, I couldn't find really my picture from the time, but I recently found my very first, passport, and it's still that was from the time, so it actually says canceled, on this, but anyway, so there was one other thing which actually happened where Kate was involved, which actually I just found out only yesterday, so, and it was kind of concurrent development. It's actually was an ICAP, the atomic physics, major atomic physics conference. It took place in 1994 in Innsbruck, and apparently in this conference, which I did not participate, there was one special session where people put all just talks which sort of did not belong to the rest of the conference. So there was 3 speakers in this session. One of them was Kate, who was already pointed out, played a big role in me kind of getting here, and then became a wonderful mentor and a friend for many years, But there were 2 more talks. One of them was a talk by Arthur Eckert, who at the time, talked about quantum computing. That was new for atomic physics community, and it really had profound consequences for many of the things which I talked about, but for the field as a whole. One other talk, which I only realized yesterday, was also given by it was something which also had played a role in both my work and many of work that, many of you are doing, was by W. Morner. It was about individual molecules trapped in solids, so. Okay, so one of and you will see how all of these things play out throughout my talk, but one direct consequence was that there was 2 people in the audience at the time. One of them was a young professor from Innsbruck, Peter Zoller, and then was even younger postdoc at the time, was Ignacio Chirac. And they knew about atomic physics, they knew about trapped ions, and they immediately could make a connection how these ideas of quantum computing could be connected with the ideas of atomic physics. And this work really, I would say, truly jump-started the worldwide effort to build the quantum computers. For the first time, they showed that realistic quantum computers can be realistically built. So the reason I'm bringing this up is that, actually I was kind of following these developments. My PhD was in quantum optics, not in quantum information. And one of the ideas which I had while coming here, I wanted to work on, quantum information. So as I said, no one was working here at this time and this, but, Kate, encouraged me to go for it. And, so when I came here, I was quite naive, and, if you think about what are the best qubits are, guess what? You will never guess. You will never guess what I thought. But it's actually obvious to you. So my background was quantum optics. Optics means photons. So why is it the case? It was, 1998, and basically the only kind of meaningful experiments, where entanglement was single quanta were isolated, and entanglement was demonstrated, was actually photons. Obviously, photons had a few problems. So first off, photons are harmonic oscillators. They're really not qubits. And moreover, photons are mostly linear systems. That means that individual photons really do not interact. Moreover, photons travel very fast. They cannot be localized and stored, and they can be scattered, and they can be easily lost. So I kind of knew about these problems, and I think maybe the most severe was the one that that basically photons do not interact. And so, as a kind of first project, I thought about what if one could make photons interact somehow. And there was some ITAMP network that I could tap in. So in fact, one of the first ITAMP postdocs was Ataç Imamoglu, whom I knew a little bit, from my kind of previous interactions. He was already a big professor at UC Santa Barbara, and I was not even sure if I can approach him about collaboration project, but Kate told me, look, you should write to Ataç and you should go visit him. And so I went and spent a couple of weeks in Santa Barbara, and actually, resulting from that, we started thinking about, how to use at the time, slow light was actually the topic which, everyone was exploring, and we kind of realized that in principle, you can use slow light to make photons interact. So, looking back, this was still quite naive ideas, but, this is, how science develops. So I should kind of say here that, this deterministic high-fidelity interaction between photons is still very challenging. And this is despite of what, some people, for example, in Australian government think, So this is still the case, I hope there is no legal repercussions to the ITAMP. Okay, so let me now to proceed. So I will explain afterwards what I mean by this joke. But sorry. So I would like to make a historical detour. So how I was a grad student in Texas, and actually, to be honest, I really did not believe that having an academic career was an option. So it was the time where like the people who led, for example, the first BC experiment, could not get academic positions. There was email was new, and there was emails sent around saying, how horrible it is, and so on. So I was really not thinking about an academic career. So what, like how did I even start thinking about making, this kind of ill, thought through phone calls to people like Kate? So this is not a trivial connection. And this connection has one specific place in mind. So this is a Cliff Lodge in Snowbird in Utah. Is a ski resort where there is an annual conference in winter, every winter for the last 55 years or so. There is a conference of physics of quantum electronics. And actually, my journey to the ITAMP lays directly through this place, which is actually a hot tub, So it is in this hot tub I met Hans Briegel, who was actually spent some time in Texas and then went here to work with Roy Glauber and became an ITAMP visitor. And actually, sitting in this hot tub, Hans told me, you should really apply to the ITAMP. So this is some pictures. So this is actually future Professor Hans Briegel. So it's his son. He's actually future Dr. Carl Briegel, who's finishing his PhD working on NV diamond magnetometry, believe it or not, So much like, Chris, who's now starting his second career on NV diamond, the young Briegel is actually going strong. So, and actually, so while here, Hans tried to work with Roy, but actually, most importantly, he met, some of the people whom I already mentioned, Peter and Ignacio, and then actually went to work with them. And one of the like major contribution at the time, they came up with this idea of quantum repeater. So their paper is very mathematical, so it's actually not really a picture, but basically the idea was that you can somehow use some memory like atoms to store information and communicate between them using photons. So it sort of at least removes some of these problems associated with this photonic quantum information. So then the next thing I want to kind of go in is we're kind of moving forward. So I arrived here and started working a little bit with attach. And then there was summer 1999, and there was a small problem. So here is actually, it's a picture of Marlon Scully, my thesis advisor. Actually, together with him is Vladlen Litokhov, another very famous scientist. I could give a full talk about him. He's actually an amazing guy. A lot of the things which are being done was proposed by him, was a Russian scientist. And so Marlon at the time in summer 99 was actually had his, I guess, 60th anniversary, and there was a big, kind of conference organized. It was organized in Munich in MPQ. And of course, they invited both myself and Susanna, who was actually here already, a postdoc at the time at MIT, actually. And I could not go for reasons that I showed before. So basically, I didn't have a visa to, to travel, anymore. So my passport expired, and I just couldn't go. Susanna also couldn't go. I could go. It's a separate story, but but none of us could go. And so basically, and there was all of these famous people coming from all over the world, and they kind of invited us, and there was no Zoom option at the time. So we kind of felt bad. And one other thing they kind of try to do, they try to organize this kind of Festschrift, a special volume with papers. And normally what you do in this volume, you write some kind of half a page, some nice story about, like your colleague, and then you put some paper that you don't want to publish anywhere else. It's a kind of a strategy, but it kind of felt lame, And it was, we felt very bad, and somehow that motivated us to kind of, think a little bit harder, right? Maybe come up with some interesting new idea and so that actually is the origin of this idea of stopped light, and trapped photons. So basically, you kind of one morning, kind of Saturday morning, in the kind of desperation and lamenting about it, we cannot travel, So we actually sort of thought about, what one can use this kind of AIT idea to just, gradually stop the photons, bring them all to the standstill. And, we basically kind of like in 2 days, we worked it out and, started writing a paper. Michael Fleischauer came here as an ITAMP visitor and sort of we also joined forces. And we kind of, we started talking to people, submitted these people, and somehow people got very excited. So, and so this journal is actually optics communication problem. Most of you don't even know that it exists anymore. So, but people started to get exciting. So we published another paper, and then another paper, and then the other thing which happened was that I went to Texas A&M to do a PhD in theoretical quantum optics. But in the middle of my PhD, Marlon came and said, well, we're doing all of this theory, but no one pays attention. So I have a great idea. I have an empty optical table and a lab. So you should go there and build an experiment, and you are in charge. But well, okay, every challenge is an opportunity. So my PhD, let's put it this way, had an experimental component to it. But one reason I never told it, when I came to the ITAMP, one thing which I was really looking for, here I can really do theory finally. I don't need to do all of this stuff. But then somehow people got very excited, and there was another, gentleman here, so Ron Walsworth. So he was a physicist here, and he often joined this coffee. This ITAMP coffee hour is a kind of central theme of this talk. And I was telling you, and we were talking about this, kind of idea and so on. And actually, I realized by using the kind of setup that I built in Texas, that one could really demonstrate it. That it turned out that Ron had kind of all components. He had some, old lasers, old vacuum cells, and then basically, by just using these components with and kind of getting a couple of people, some of them was actually, Annette was Michael's wife, who was a physicist by training. He did not work for maybe 10 years or so, but she had they had a daycare, so she joined the effort. So we actually, in just a couple of months, demonstrated this idea, and it really started a big new research direction. So it landed on the front page of New York Times, and it was like people got very excited about this. So, yeah.
At that time, I saw internet kind of a reaction on what Misha Lukin left. From Russian lab, it was a beautiful message. Okay, slow down light, it's not problem. In our lab, we accelerated it.
Okay, so this timing should be counted towards questions. But there is one it was clearly it was kind of an interesting and cute kind of demonstration, but there was one problem. So if you really want to build quantum information system, you don't only need to localize photons, you need to make them interact strongly. And in this kind of slow light experiment, so basically the stop light experiment, the photon is stopped in a spin wave, delocalized over atomic ensembles, which are actually effectively bosonic excitations. And so they are not interacting, so you don't really solve the interaction problem. So, but you are now, the excitation is stored in atoms, so maybe you could try to make atoms interact and make them sort of, do some kind of quantum logic. This actually, I was kind of thinking about that in parallel. In fact, this was at the time already the idea of can you use neutral atoms more generally as some kind of carriers of information as a qubits. And there were two challenges. One is it was difficult to isolate and control atoms individually, and the second that they, in the gas phase at least, they interact very weakly. So some of the first clumsy attempts to kind of solve this was actually kind of some work that we've done in collaboration with Phil Hammer. Again, most of you probably don't know him, but Phil was actually one of the pioneers, for example, in using NV centers. So he was at the Air Force lab. He was actually Susanna's postdoc mentor. And at the time we started thinking about, okay, what if we take these, two impurities and bring them very close, tens of nanometers apart, have them kind of interact and so on. So it was really kind of very naive, very early ideas. So, and then another thing happened later in this 1991. So we were visiting Robin, he's somewhere here, next to Vasily, as you know. And we were, actually it was kind of, well, okay, so it was, in Canada. So actually I somehow got in there. So, you remember I could not travel, but I thought I could travel in Canada. Well, actually it turns out in Canada, they can, so they stopped us at the border, and we were going to the Christmas dinner. They stopped us at the border and said, "Look, you cannot, go to Canada. You can go back to New York City to the Canadian consulate. Maybe they can give you a visa." And we said, "Look, we are going to this special family. They have 9 kids, and a mother cooking great." You cannot. And so this guy looked through the rule books and said, okay, so there is one exception. So if we can let you go without a visa, but then you have to pay $200 fine, And that's how we got in. So, and then we had a wonderful time with Robin. And then, eventually we ended up in Quebec City. And I hope I got it right. It's a kind of a famous hotel, basically a big, castle. And, and we were walking around with Robin, and I should say that, we were a little bit, not under influence, but, under hangover, let's say. So it was a few drinks and a few more drinks and a few more drinks, and then while wandering around this castle, I kind of complained about the fact that, okay, the atoms don't interact, and Robin had a training with Alex in atomic physics. So, well, there are these Rydberg atoms, And so these Rydberg atoms, they seem to be like, this, not completely sober people kind of wandering around, maybe not in circles, but in these ellipses. But, because of that, they can kind of interact, So, and so that was another important, point of this journey. It's all disconnected things. I promise they will come together. So, and then in the spring of next year, I actually first met in person Peter, who was here in as a part of the ITAMP advisory board, and actually also later that year I met Ignacio Chirac, and we had like two types of interaction. One was actually very cool, and another one was not so cool. So I first give you good news. So first off, he, of course, and actually Luming Duan was also one of their postdocs. So we immediately started thinking about how we can use this atomic memory to realize these quantum repeaters. So the result was this the so-called DLCZ protocol, which actually kind of resulted in a kind of new research direction of really trying to build these networks, build quantum repeaters, and actually this, had a influence, through several generations of ITAMP postdocs. So one of the first postdocs, ITAMP postdocs I ended up working with was Anders Sorensen, who then together, with Jake and, Lily, was actually some of my two of the first students, thought about using this kind of solid state emitters, like molecules that W. Werner talked about, frozen as information kind of carriers, as storage. I should say here that throughout these last 20 years, I was really blessed with an amazing generation of students, and actually every new generation is better than the other, and at some point you cannot believe it can be better, but it's actually still going on. So I don't know how it can happen. So Jake was one of the very first students, but he was, and the reason why he ended up working with me is that he was an undergrad at ITAMP and worked, I think, with Alex and maybe Jim, and then, so they somehow told him to maybe, talk to this new guy, and that's how it happened. So, but then basically Paolo joined the effort, and she brought the knowledge of this NMR, which actually kind of also played a big role, and and then eventually we kind of started doing experiments in this area, and actually it still is a vibrant direction. So just kind of a most recent progress. Just today there are two papers in Nature, one, and they're both using this kind of idea of this, memories connected by lights to build, to demonstrate world's first metropolitan quantum networks. So one of them is actually here in the city of Boston. It consists of two nodes. They are basically like in two different floors of the Lisa building at Harvard, but they are connected with the fiber loop, which actually crosses Charles River 6 times, And it has it's really sort of it's a real world network. And so actually another one is a paper from, that one is using silicon vacancy color centers in Diamond. Actually, in the back-to-back today is a paper from Zhang Wei group from China, which actually uses this good old DLCZ protocol. So it's all, situation is developing, we call it. So, but this work on kind of solid state defects had also a lot of other kind of new directions. So, including, for example, ideas of magnetometry that, you heard a little bit already from, or quantum sensing that you heard from Chris. So when Peter arrived, we started thinking about, using this, also, basically exploring the solid state systems in combination with quantum transducers. And this actually is still a very cool, very vibrant direction. So basically with ideas of biological sensing, of material sensing. So for example, Richard contributed to that. And in fact, some of the, this actually new paper is just coming out, where we are thinking now about to use these ideas to really make a kind of hopefully scalable, solid state processors. But okay, I'm getting a little bit carried out. So let me go back to this, my interaction to 2022, when I met with Peter. So I told you that there were two parts of this conversation. One was good, another one was not so good. So the not so good part was that I told him, we're also thinking about these Rydberg atoms. And he was listening very, very carefully and started asking some questions, which made it very clear that they are not just thinking about it, but they're in advanced stages of working on it, And, Peter at the time was already, clearly a leader in the field, And I was not in a good mood after that, So maybe Robin remembers it, But somehow we we realized that we're thinking about similar ways, but a little bit complementary. And if we put these ideas together, something very special can come out. And this was the idea of this Rydberg blockade. I will explain it to you in a second. So this Rydberg blockade is actually a central feature of my talk, another central feature, which resulted in many different, cool directions. So one of them involved this kind of idea of making single photons interact strongly. So there you could just, by coupling photons to atomic ensembles and making atoms in the ensemble interact strongly through Rydberg excitation, you could really make them interact. So we started this work with Vladan initially following this kind of our idea with attach, but very quickly we realized that if you just sort of excite the atoms in a Rydberg state, just invert this lambda system, make the excited state being a Rydberg state, you could really make single photons interact. And already, Thomas already was here and had a lot of contributions, and it really resulted in a whole series of different directions. So this one is a paper which gained kind of notorious traction for comparing it with lightsabers. So basically, two beams of light would influence each other at a single photon level. And then there was, new generations of postdocs who really pushed it into completely new directions, like, Rivka and Igor, these kind of ideas of quantum metasurfaces and things like this. So one other question is whether you can use these ideas to build quantum computers. So and to kind of, step back a little bit, so when you do cold atom experiments. So typically what you do, you start with something which is called magneto-optical trap. It's a kind of a workhorse of essentially every cold atom experiment. And typically when you trap and cool atoms, you end up with the cloud which looks like this, which contains typically some tens of millions of atoms. So it's a lot of atoms. So if you could somehow isolate and control each of them, it's a lot of qubits. So basically these cold identical neutral atom qubits are essentially unlimited. The key challenge is inefficient classical control. And about 10 years ago, we started an effort to try to, figure out if we can control single atoms at scale. And the idea was to start basically with optical tweezers, which has by then been very well-established technology, and essentially focus these tweezers so tightly that you can, at most, in each tweezer contain one atom. And so, but the idea was not to start with one tweezers, but start with many. By now, we start with thousands. And so when you do that, when you try to trap atoms, what you end up having? You end up having a situation where some traps will be full and some are empty. And this system, as a result, has an entropy. So, but one elegant way to get rid of the entropy is to essentially take a picture of these atoms, figure out which traps are full, which empty, and then just utilize the knowledge that some traps are full to just rearrange, to move atoms around. So, for example, you can remove some traps and move them around. And so with this situation, you end up with the atoms sitting a couple of micrometers from each other. They are very well optically resolvable, but they also don't interact. So this system is completely classical. So to make them interact, this is where Rydberg atoms come to the rescue, and this has been a really kind of an amazing project. It's actually a collaboration between my group, Markus Greiner, and Vladan Vuletic at MIT. So that's this idea of Rydberg blockade. Let me explain it a little bit, that we actually developed a time in collaboration with Ruben and Peter and Ignacio. The idea was the following. So suppose you have atoms and excite them to in a Rydberg state, and suppose that these atoms are sitting very, very far away. So in this case, the atoms don't interact, and the lifetime of Rydberg states is actually decent. It's about some hundreds of microseconds. So you basically, in these conditions, if you have a good lasers, the atoms will just undergo independent Rabi oscillations. However, what happens if the atoms come closer together? At some point, this super strong van der Waal interaction really takes over. And what will happen is that it will basically shift the states where you have two or more atoms excited in a Rydberg state. So at this point, you will be able to excite one atom or another, but never both of them together. So the simultaneous excitation is blocked at distances smaller than this Rydberg blockade radius. And it turns out that it's an amazing mechanism to entangle atoms. To the leading order, it's insensitive how close the atoms are. It's insensitive to their motion. So basically, what this Rydberg blockade does, it makes this interaction between atoms almost digital. So if the atoms are far away, they don't interact. If they are close to each other, the interaction is almost like infinity. So it's basically, it's very, very strong. So all together, putting this all together, so what you end up with the system, like this. So you basically start with some disordered array of atoms. You create some registers, and you subject these registers to different kinds of pulses, a microwave, radio frequency, sometimes you excite them in Rydberg state, and then in the final round, you just read the state of the atom in a way which depends on the state, in a state selective way. So basically, it's a projective readout. So this is by now kind of an exploding research direction. So there's at least 200 new experiments I built around the world. I stopped counting, and there's at least eight companies which are trying to commercialize this technology. So these systems can be used in many different ways. Actually, one of the ways, stems from the work of, several generations of ITAMP postdocs. So Anna Maria already pointed out today in the morning that, when she was here, we started thinking about various kind of spin systems. So it's actually, this work was inspired by earlier work with Jake and others of using like quantum dots to encode qubits. But, with atoms, you could clearly do similar tricks, but with much larger system. And you could study various types of dynamics. You can, for example, study localization. So this actually is another example where multiple ITAMP postdocs contributed to a project. But I think one of the papers which really sort of stimulated some subset of experiments was by Thomas. So where he actually came and said, oh, okay, if you start with Rydberg atoms, exciting them, you can create these Rydberg crystals. And so this actually is one of the very first experiments we've done with this atom array. So basically at the time started with just a linear chain of atoms. And then one could think about a linear chain being excited in a Rydberg state as a kind of like a spin model. So it's basically an Ising model where you can have the driving term is just filled effectively in the x direction. There is this detuning term, n is the number of atoms in the excited state, and this is the interaction. And you can ask what will be the zero temperature phase diagram for the spin model. So clearly it depends on two parameters. One of them is the detuning, and another one is this interaction range. So if there is no interaction, depending on the detuning, either n's all has to be 0 or n's has to be 1. So this is a term which minimizes the energy. But clearly, if you have a nearby blockade, this configuration is clearly energetically unfavorable. So if you have just nearest neighbor blockade, what will happen is that the lowest energy will be a state where every other atom is excited. So it's exactly this Rydberg crystal that Thomas has proposed. And if you have a longer range interaction, then every third atom is excited, and etc. So, I mean, it kind of seems obvious now, but actually at the time when, Thomas started thinking about it, it was really completely non-obvious. And there were actually long discussions about, can these states ever be created? Actually, it turns out it's very easy to create them. All you need to do, you need to start with the ground state atoms, adjust your interaction range, and just change your detuning to adiabatically enter the states. And this is actually some of the very first experiments we've done with the system. So here, you basically change the detuning, and then system goes basically through the phase transition. You end up in the either in this up, down, antiferromagnetic state, or the state where every third atom is excited, and etc. And so basically, this is an example. In fact, more globally, going back to this original idea of Feynman, of using quantum systems as quantum simulators. So here, by programming in interaction, you can really break different types of symmetry. One other thing, which actually was also one of the very first experiments, is to try to kind of play with system kind of dynamically or change parameters non-adiabatically. And this was inspired by some of this theory work on kind of how fast system formalizes. But actually, when we kind of first tried to do this experiment, and it was really just a kind of a warm-up experiment, so where we first create this crystal and then rapidly change the tuning to basically try to see how system will formalize, we saw something very funny. So we saw this order, which we initially create, it disappears. But then if you wait for some time, it actually reappears. It disappears, it reappears again. So basically, if you look at the order parameter, it really keeps oscillating. And just to really show you that this actually is a kind of a shocking observation. So this is like starting with a crystal, putting it in the hot water, it melts. But then you wait a little bit, it reappears. It melts, and it reappears. And we were very, very puzzled. And actually, remarkably, it turned out that the explanation goes back to Rick Heller, who was an ITAMP director at the time when I came here. So, and we now understand that there's a kind of many-body version of this kind of something which is called quantum scars. It's basically the phenomena which, in a chaotic system, there are a certain number of unstable but long-lived orbits. And this actually, one can sort of in a modern language understand it in a language of matrix product states. And the person who really figured it out is actually Hannes, along with my student Sun Won, who is now at MIT professor, and Maxim Serbin, whom many of you also know. So this is just one example. As I already mentioned, this is by now a very exciting direction. There are different types of atoms are being explored in molecules, and actually some of the systems become very fancy. So this is a two-species array with Hannes Bernian group and in Chicago, who is now moving to Innsbruck apparently. So if I can say that. So, and this is the image of over 500 trapped atoms in a Manuel's group at Caltech. And this really is a very exciting frontier because it connects many body dynamics to quantum computing, to quantum metrology, and it's very much complementary to other developments in these fields like optical lattices. So in our lab now we actually are operating third generation of the array. And the kind of way, the way how this experiment works is that it uses this device called special light modulator. It's basically a computer-generated hologram, very much similar to the device being used in this projector to project the static traps. And then we use other channels which introduces dynamic traps. So this device called acousto-optic deflector is one which allows us to move atoms around. And in this third generation, we have larger systems, high fidelity, and more advanced control. We trap over 1,000 atoms and can make defect-free arrays of now over 500 atoms. So with that, we had a lot of fun last few years and explored a lot of different directions. I already mentioned both different phases. Now we're working, of course, in 2-dimension. We have looked at dynamics like scars. We also created new exotic states of matter, like this something called topological spin liquids. And actually, by now, you can do these kind of experiments without leaving your office or home, because there's actually in a startup company across the river, they have a system of this type that I just described. It's actually available online. So I will just talk about one example of recent work. So most of this work is actually using kind of analog mode. So I will focus now on the digital mode, and it's connected to something which is called quantum error correction. So to motivate that, let me just step back here and ask what's the key challenge that this quantum information processing is facing, and so what limits our ability to execute large useful algorithm at scale. So you could say, well, it could be number of qubits, but as you already saw before, we now have hundreds or even thousands of qubits available. It's actually could be quite powerful system, so we can make a lot of operations. But what really limits it is that after a certain number of operations, if you make errors in like logic, for example, in a gate, what will happen is that your basically output of your quantum computer is just garbage. It's completely just dominated by these errors. This is something that people early on kind of realized. So now one could make maybe hundreds or maybe thousands of operations without error, but for most useful, interesting algorithms, they require a lot more. They have like billions of operations, sometimes many billions. So these errors is a fundamental issue, and this has been recognized very early on. One key development which really jump-started this field was also in the mid-90s, was this idea of quantum error correction. So quantum error correction basically uses the same approach as the classical error correction, is to use redundancy. So for example, instead of 0, just one physical qubit, you can encode a 0 state in 3 zeros. And then you can use some kind of majority vote to decide which, if the state is good, or not. And of course, extending it to quantum domain is non-trivial, because in quantum domain there is no cloning theorem. You can also not measure the state without destroying it. So it seems that quantum error correction is hard, but actually it turns out to be possible. And the idea is you can basically use entanglement to localize quantum information over several physical qubits to create, for example, one logical qubit. Logical means that this qubit should be protected. And the way how you protect it is you basically measure something, what's called stabilizers. These are basically some kind of local parity checks, doing what sort of, this you do kind of classically, but in a kind of non-destructive way to basically check if the error has occurred, and if so, when. And so in this kind of redundant encoding, if the error occurred, you can actually correct it. And by being delocalized, this logical qubit degree of freedom is hard to accidentally manipulate. And this is actually this pioneering work by people like Peter Shor, Andrew Steen, and Alexei Kitaev, John Preskill, and many others. So this seems to be like a very exciting direction, and that's when people started thinking seriously about quantum computers. But actually, around the time, so it's this time is August 1996. Remember all of this. Around the same time, there was some people who were leaders at the time in creating largest entangled states, who really pointed out that like these ideas are very far-fetched. And the idea is the following: so basically, this quantum error correction, what you do, you basically build a small Schrödinger cat codes, states. These are these error correcting codes to protect much larger cat. And but this making cats is actually kind of a losing proposition to begin with. And so in fact, what they pointed out, we think it's fair to say that unless some unforeseen new physics is discovered, the implementation of error correcting codes will be exceedingly difficult as soon as one has to deal with more than a few gates. So this comes, remember, this comes from these people who are really the leaders. And in fact, at the time, we were working on Rydberg atoms. And guess what? They were largely right. So it's actually, these logical qubits are very hard to build and control, especially. And up to now, the demonstrations were really limited to one or two very small qubits, and maybe at least one, at most one gate operation. So let's see how we can actually address this problem. Here again, ITAMP comes to rescue. So, and the idea is the following. So we basically, actually, how much time?
You're way past it.
Well, I had an hour. Oh, no? We didn't start.
I mean, just keep on going.
All right, so I hope it's an entertainment. So I had an hour and we did not start at 4:30. So it was not so bad. I don't like it in the middle. I can stop at any point. So okay, so you just okay. So anyway, okay. The idea is that to really make a good logical qubit, it was clear that we need to store the information in like hyperfine states, which we can manipulate very well, and only for a short time we should excite atoms in Rydberg states. And this was actually this early paper, with Peter and Ignacio. And the problem was that people started doing these experiments, and it actually did not work very well. So for almost, for nearly 20 years, people entangled atoms, but the fidelity of entanglement was actually very low. There was a lot of errors, and for this reason, if you would ask like 5 or even 3 years in the community, what about this Rydberg atom approach? People would say, oh, it was a cool idea, but guess what? It just does not work. So this has completely changed now. So what has happened? So first off, this was an advance which is now called Levin-Pichler gate, which was developed by Hannes, and he was working together with my student Harry Levin, a newly minted Berkeley faculty member, and actually all it needed is one good idea. So Hannes had a good idea, and Harry implemented it the same day, and it actually was way above all kind of expectations. And I should say that this idea they had when I was ITAMP postdoc, I really spent like a couple of months thinking about how to do it, and I just failed. And it was not just me; it's also all this Luming, Duan, a lot of Dieter Jacques, Peter and Ignacio. We really tried to figure it out. And so basically what we try to do is we try to basically make this gate by just addressing atoms, jointly, collectively, and just using basically one pulse. But what Hannes pointed out is that if you install one pulse, you just use 2, and you change a phase, then you can achieve this is controlled phase gate. You just apply the phase conditionally on a state where both atoms are in the state 1. So. And as I said already, the same afternoon they implemented it, and the fidelity went from 80% to 97.4. And this was one kind of innovation. The second innovation was the realization that if the atoms, if the qubits are stored in a hyperfine states, then not only the storage time can be seconds, can be very long, but you can also move qubits around. By just moving tweezers around, you can basically make the architecture of the processor kind of a living organism. So normally, if you build a processor, if you build a chip, you design it first, it goes to optical lithography, actually uses CMOS technique, you write this chip, and that's it. It's fixed. So if you want to change the connectivity, you need to build a new chip. So here, we can actually change the connectivity, the architecture, during the information, the kind of processing itself. So it has really unique opportunities. In particular, has non-local connectivity and has also parallel, really efficient classical control, as you will see, is a key. And so the first kind of example, the first glimpse into that was already a couple of years ago, where we actually prepared, this famous story code, which was invented by Alexei Kitaev, on a torus. And you could say, well, so this story code involves this kind of data qubits and these ancillas, which make this local parity check. And you could say, okay, I can believe you can make it, but how do you do it in a two-dimensional system with a torus? Well, so here is a movie which shows how to do it. So basically in this movie, what happens is that you have these ancillas which are moving now. And so first they locally touch nearby atoms, and then they move all the way across. And that enables one to make this kind of torus connectivity. So that's the idea. And the key feature of this movie is that we can create here two logical qubits by essentially just using two control parameters. These are the voltages which specify vertical and horizontal, position of these qubits. This efficient control is really the key. So in the last year, we were quite busy. We made a number of technical upgrades. First off, we improved the fidelity even more. So it's now basically competitive with the best fidelities across all platforms. So it actually uses generalization of Hannes' idea to make a smooth pulse, but with a changing phase using these optimal control methods. We now have also universal control by using these acousto-optic deflectors. We can actually do hyperfine Raman rotation for any pattern, for any set of the qubits. And we also have this other important thing. It's called mid-circuit readout. So you need it for error correction. So what we can do is we can just pick some atoms, move it in the readout zone, and basically read them out without disturbing the others. And so when it all comes together, is this first realization of what we call a logical quantum processor. So in this logical quantum processor, we have these zones. One is this storage zone. One is this gate zone, this parallel entangling zone. Another one is readout zone. And actually, if you think about it a little bit, it now finally starts looking like a real computer. In fact, it's very reminiscent to something which is called von Neumann, but there is even more. There is something which is called Harvard classical CPU architecture. So, okay, so this is about half time of my talk. I thought I have an hour, so maybe 10 more minutes or so. Okay. Paul, you tell me. You're the boss.
Sure.
Yes.
Correct.
Yeah.
Okay.
Yeah.
Move forward.
Yes. Okay. Good. Okay. So, all right. Okay. So I'll show you different types of data, but I mean just one key idea is that we now want to move on from controlling physical qubits to controlling logical qubits. And the illustrative example here involves entangling gate between two logical qubits. So remember, in these logical qubits, the quantum information is delocalized. And this is good for protection, but it makes it also very hard to manipulate this information. So normally, to do a gate, for example, what you need to do, you need to basically make sure that each of these qubits on the right can feel the presence of each of the qubits on the left. And normally, this is very hard. You need to do a lot of swaps and kind of individual gates. And actually, if these individual gates are faulty, you need to make a lot of rounds of this error correction, a lot of rounds of this stabilizer measurement. But there is another approach, and this is so-called transversal gate. And this approach, what we could do, we could just directly interact the localized degrees of freedom by just taking one patch, bringing it on the top, on another, entangling them all in parallel and separating them. And at this point, we actually implement the controlled NOT gate. It's one of the entangling gates. And the beauty of that, in this approach, this gate is inherently fault tolerant. What it means is that the errors don't spread within the block, so you actually need much fewer rounds of error correction. So you also can have this also enables long-range direct connection between logical qubits, and actually it's a significant savings for large-scale algorithms. But most importantly, at this point, we start to really think about this, patch as a kind of a macroscopic atom. So we basically, here all qubits in this patch receive the same instruction, so they act like one big macro atom. So that's the idea. So a couple of examples, one is basically demonstrating this logical CNOT with this surface code. It's like a toric code. So here what we do is we start with these two code blocks, encoding 2 qubits, and then prepare them, one in a state plus, another one in state 0. And then, basically what we do is what I described. We bring them on the top of each other, entangle, move away, and then, measure. And of course, what we can now do, we can start with the small logical qubit, increase its size to a little bit more, increase its size a little bit more, and see if our gate improves. I mean, that's a key property of quantum error correction. The larger you make entangled state, counterintuitively, the better your operation is. So here, what we show is that 2 of these distance 7 qubits are entangled. Up to now, people were able to make, I think the largest was, distance-wise 1 qubit by Google. It was a very celebrated paper from last year. So, but most importantly, as we increase the code block, what we see, our error decreases. So that's a key property of quantum error correction. There is wide variety of technical caveats here that maybe you don't want to know about. So it turns out that we have to decode these qubits in a joint way rather than individual way. There is also, we just did one round of, in principle, one need to do many rounds. But really, what it shows you already that like the basic ideas of error correction are really clearly show up here. And this is also an exciting frontier. For example, the fact that one has to decode these qubits jointly rather than individually is sort of obvious past the fact, but this was not really realized. So there are other things which we can do. So here is another way of how to do, how to prepare good logical qubits. So here you basically start with 2 codes. They're called color codes. It's a little bit different code. So you entangle them, and of course when you entangle, you make errors. So it's so-called non-fault tolerant preparation. But then what you could do, you could use a pair of them and use one of them as a kind of a flag to check if the other one was prepared. So it's basically like a Ramsey experiment, but now with logical qubits. And so basically by entangling them and kind of then just measuring one of them, if you measure this one is in one state, in a 0 state, you really, with high probability, know that the other one must be 0. And actually, in that case, for example, we can initialize our qubit with fidelity, which is much better, which is about an order of magnitude better than what we can do with physical qubits. So experiments like this with 1 or 2 qubits have been done previously, but our system allows us to do it with many more. In fact, this data is an average of 4 pairs. And of course, once we prepare these 4 qubits, we can start doing experiments with them. And so one of these experiments is to prepare a logical GHG state of this. And we see immediately that we've used fault-tolerant preparation, or if we start doing some more tricks like being error detection, we can really push the fidelity all the way to 1. So this is actually one of the first examples of algorithm with logical qubit, and one already we see that, for example, usually with physical qubits, if you want to test GHG experiment, you measure parity oscillations. Here you cannot do it. These things are digital. So, but for that, for example, you can do a state tomography and extract all of these things. And so this is actually really kind of brings me to the last part of the talk. So we are now entering this era we call the era of early fault tolerance, where we start really thinking to build and test logical processors in a lab. And what's actually exciting here is that one really, if you want to do something meaningful, you need to think about like the task you want to accomplish, the algorithm, and find a good error correcting code and match it to your hardware in a way which is called co-design. You also have to find the optimized decoder, optimized compiler, and this is a sort of an obvious consideration, but the field as a whole really kind of missed it up to this point. So one example, now it's a little bit for experts, I'm so sorry. So this is implementation of some so-called non-Clifford operations. So non-Clifford operations is the operations, for example, when you rotate your state by a phase which is different by pi over 2 or pi. This pi over 2 or pi is a kind of like, is a digital value. But for example, pi over 8, it turns out from pi over 8 you can create you can have any basically from two pi over 8 gates, you can create, rotation with arbitrary phase. It's really kind of, makes, what makes quantum mechanics kind of in some way powerful. And so to actually do it with the, to do these non-Clifford operations with logical qubits, it turns out to be very hard because logical qubits are kind of digitized rather than continuous. And normally you have to do all of this kind of, different types of, shenanigans. So for this reason, it's actually called quantum. This non-Clifford operation is called quantum magic. It's what gives magic to quantum computers, basically. So, and for 2D codes in particular, it's actually very challenging. But the question is, can one generate magic in an efficient way? It turns out you can do it using 3D codes. You could say, well, 3D codes are hard for you. But remember, with the configurable architecture, the geometry does not really have any meaning. So in fact, what we do, we prepare this, these 3D codes with basically qubits connected like this on a cube. And it's actually realization of the three-dimensional color code, is so-called 832 code. It's called the smallest interesting color code by some people. And actually what is special is that, this color code enables this non-Clifford operation, for example, CCZ operation. You can do it by just rotating individual qubits in this cube. Okay, so the algorithm that we'll just implement, and I will finish soon, I promise. Yeah, so we'll prepare logical state and plus state, and we'll do this CCZ and CZ within a block, then entangle blocks together, and then repeat it many times. So it turns out that this implements the so-called scrambling circuit. It just entangles all qubits with all. And in fact, what we'll do here, we will implement a circuit. We'll target the connectivity of high-dimensional cube. So remember, our qubits are already cubes, and we will make 4-dimensional cubes out of our, well, it's in total will be up to 7-dimensional cube, okay? So, and actually it turns out that, the output of the circuit is, is a kind of a quantum a class of quantum algorithms called instantaneous quantum polynomial, which actually creates highly entangled states, which is actually known to be classically simulated. And what we'll do here, we will sample from this state. And so this is an example. So this sampling is like a speckle pattern, if you want. So it produces kind of a random pattern. So what we show here is, is a small system for 12 logical qubits. Theoretically, we expect some distributions, kind of random, strings like this. So if we do it without error correction, what you see, well, maybe there is some correspondence, maybe this peak corresponds to this, but it's very hard to see. But now we turn up this error correction, in this case, error detection, actually. And what you see is that a shadow of this ideal distribution appears. And this actually can be quantified. For example, you can look how fidelity increases and so on. And what we have done, then we try to scale it up, and we went all the way to up to 48 logical qubits. So this actually is a logical circuit, which we have created. And in this case, still we see that this encoding and error correction still improves the performance of this circle. This actually this circuit. This is actually a physical connectivity which we implement, and in fact, this really is very meaningful. So it's at least an order of magnitude larger than the best possible fidelity we could obtain with our most optimistic numbers, and actually it's the best fidelity which that in any experiment has been done. So in fact, this movie shows actually how we implement this circuit. And what you see here is that we kind of entangle these qubits in a hierarchical way, in bigger and bigger blocks. So here we run out of space in the entangling zone. We drop it now in storage zone, bring another one, and look at this now. So we entangle things locally first, right? And then a little bit more globally, a little bit more globally, a little bit more globally. And then in the last state, we entangle them all. We bring these qubits from the storage zone and entangle them all. So this is by many measures the most complex quantum computation which has been done today. And so we are now already starting to think how we can use this. And actually one cool idea here is to measure this, entanglement entropy in the scrambling circuit by also using the ideas that from Hannes' PhD. The way how you can do it is just by starting with 2 copies of the state and then make the measurement of these 2 copies in a Bell basis. And here what you see is that basically it's like the system behaves like in a way akin to the black hole. It's not a black hole, but so you see the entanglement entropy grow up to the point where it's half of the system size, And then, because the global state is pure, and particularly if you include this error correction, error detection, it turns around and becomes pure. And basically, what we think is now is the starting of kind of a new era where one can really start exploring physics of complex systems. Kind of there are new, exciting scientific opportunities with fault-tolerant processors, and then the new generation of theorists at ITAMP, Christian and Stefan, are kind of leading the way. So I kind of used up my time, but I hope you kind of you can see that this actually the field of quantum computing starts to face a bright future, and we see a clear path to experimenting with maybe up to 100 logical qubits with error rates 10 to the minus 6 or so, with just using current techniques, but also with the kind of new developments, new additions done with some of the people who are mentioned, like Jiang group, for example, at Chicago. We are also starting to explore path to systems with thousands of logical qubits and much larger circuit depths. But to kind of see why I think this is a kind of phase transition in the field. So this is a drawing made by students who built and run these circuits, and in this drawing, so it's a GHZ state. So they are now thinking about implementing this GHZ states, implementing algorithm with logical qubits. Each line here corresponds to logical rather than physical qubit. And this actually is very exciting. I think this is exciting interface at the direction at the interface of science, engineering, and applications. And I think we will see some really cool developments in next months or years. So, okay, I used up my time. So I would like to thank the people whose blood and sweat resulted in this work, in particular in the second part of this talk. Also, many thanks to many generations of ITAMP postdocs and visitors, whose ideas resulted in this, and also happy birthday, ITAMP. Yeah, thank you.
I would say 2 quick questions, and then we can continue the discussion in the poster session. Want to directly go to the poster session with reception, I imagine.
Happy to answer questions about history or about the 2 parts.
Sure.
So I guess I'm curious how to make a quantum network out of this. So in this very particular platform, would you think of adding, I mean, I think you also mentioned the networks, so you add cavities and then connect them with photons, or what's the way forward?
It depends on the scale of a network you can make. So if you want to make a local network within your vacuum cell, you can just move atoms around. But if you really want to connect things over kilometers, you clearly need to couple the atoms to photons. And there is now quite a bit of effort, including in our group. So the best thing, of course, would be to use some kind of cavity, or maybe cavity array, where you can take a bunch of atoms, move them into the cavity field, and then entangle with photons, and that's the way to do it. So I think there's an active research direction. Yeah.
Okay. Let's thank Misha. Let's go to the poster session.